vamos a empezar. Let's start because I think it's because there are exams, but there is already. No, the thing is, your slides are not, pictures are not. Yeah. Okay, maybe you use your computer and we. Okay. Yeah, vamos a usar su computadora. Si no se ve bien. Y como se ve. So you have the wire? No, I don't have the cable. Okay. Do you have the wire? It should be there because you haven't. Okay. Sorry, everyone. We will start in 2 minutes. Oh.
El gesto de la cámara.
Ah.
Sí.
¿Qué hago?
Vamos para enfrente de este, ¿sí?
Cámara. ¿Ya estoy?
No, sepárate un poco más.
¿No quieren? No creo que yo soy la speaker.
Sí. Ahí sería.
Ah, ok. Sí. Machistas.
Ya te voy a seguir.
Okay. You're ready? Okay.
Quieres que no siga y a lo mejor se apunta a la pantalla directa.
Ah, mejor. Luego sí, cuando termine, ahora ya.
Es para que ya de una vez como que es que no veo cómo queda.
Ya.
De lejos.
No importa.
No.
Tú no puedes controlar para hacer zoom, ¿verdad?
No.
Okay. Okay, so we will circulate the slides after the seminar, or maybe we can circulate during the seminar for the people interested. Just send a mail to ESF and I will circulate them so you can follow. So today we have the pleasure of having Yashmitha Kumaran. Sorry if I didn't pronounce it well. So she's a postdoc at Instituto de Astronomía at UNAM. She did her undergrad in the aerospace engineering from Amita University, India, and then he got there an astrophysics degree. She did move to the masters in cosmology in Sussex under the guidance of Marsh. And then she did a dissertation on the production of gravitational waves from early universe due to the first order phase transitions. Later on at the Eastern Mediterranean University in Northern Cyprus, she finishes the doctoral thesis on weak deflection angle via Gauss-Bonnet Theorem under the supervision of Ali Okun. So she is currently working on modified gravity theories under the mentorship of Sergio Mendoza. So thank you for coming, and you can start whenever you are ready.
Good afternoon, everyone. Thank you for being here, and it's a pleasure to be presenting today. I'll be talking about the weak lensing via Gauss-Bonnet Theorem. This was majorly my PhD thesis, so this is something that I have invested a lot of time on. So, today, what I'll be doing is I'll be giving a brief outline of what this research is about and where this is heading to. So, next slide, please. This is the outline. So after a brief introduction of the basics that I'll be talking about the Gauss-Bonnet Theorem, which is the fundamental foundation of this. And then I'll be discussing 4 different black holes and how the Gauss-Bonnet Theorem applies to each black hole and how different scenarios of each of them change the results of whatever I'll be discussing on. Next one, please. So I would like to start off with the basic. What is gravity? It's one of the fundamental forces. And Sir Isaac Newton discovered it when he was sitting under an apple tree. And the interesting part about this is so many people have fallen, many things fall, but Isaac Newton was the first one to ask why. And that is something that is very interesting for me specifically. then that's why I included that picture. And we have the two forces that attract each other, and it does not account for various gravitational effects. Then we have Einstein, who proposed the general theory of relativity, and the curvature of mass he included it as the space-time fabric. And then there are sayings that says matter tells light how to move, and light tells matter how to behave. So, and this theory answered the existing questions and more consistent with discoveries. Next one, please. But like any theory, this is not perfect, so we need more corrections to it. So next we have the basic of black holes. We say gravity is the weakest force until we talk about black holes. So when we talk about black holes, it is the gravity no longer becomes weak. It is the mass of the gravitating object as it increases, gravity increases, and that's why black hole is highly important when we study gravity. As black hole is an object, it is of dominating gravity, extreme mass, infinite density, and no volume, and it collapses on itself and concentrated at a single point. And according to GR, there exists a region of space with extreme gravitational pull. So we have here how a description of how gravity changes as we go closer to the mass of the black hole. And then how does it form? It forms when a massive object collapses on itself and creates a singularity at its center. And it's surrounded by the boundary called event horizon. And many people have put work on its Schwarzschild curve. And Einstein was the starting point of it all. And we have observations these days from LIGO and EHT to confirm all this. The interesting thing about this is Einstein predicted black holes in the year 1919, and EHT confirmed it in 2019. So it's 100 years of research gone there. And though Eddington confirmed it very early about these things with solar eclipse in Principia. So it's like 100-year gap between these two. So yeah. Then we have the question, can gravity bend light? And the simple answer to that is yes, it can, just that it bends the path of the light. So the light itself appears to be bent. So we have a star, a white dwarf, neutron star, and a black hole. And it's so profound, the gravity, that the light cannot escape. Next, we have the important theory that has gone into this, which is the gravitational lensing. A black hole is surrounded by an accretion disk, and in which the matter, dust, and photons are stuck in unstable orbits around it. So the more unstable, the more moving, the dynamic the accretion disk appears to be. And this not so circular photon sphere gives the bending of light due to gravity. And this is known as the phenomenon of gravitational lensing. So in the phenomenon of gravitational lensing, it is particularly classified into strong and weak, but I will be specifically talking only about weak lensing. So it's a pictorial description of weak gravitational lensing in particular, and how it acts as a lens and bends the light. And this was, of course, given by Eddington from the ident of Principia alone. Yeah, so why weak lensing, and what is so great about weak lensing is that it's a consequence of general relativity itself. It arises from minor distortions, unlike the strong lensing, which just appears as a whole lens together and it gives a good look into the source. But because these are too small to be detected in terms of magnification, we can see the subtle properties of the lens and the source itself. So it is sufficient enough to distinguish between mass distributions because of those subtle differences. And it possesses the property of differential deflection, meaning that it chooses to deflect certain parts of it. So it looks like it's differentially deflecting, and that gives us an insight to what comes out of what we can learn from that deflection. And the bending of light that enables the exploration of cosmic structure deeper. So the more we look into the differential deflection and study them, the more we can understand. So the angle at which the bending occurs is what we call the bending angle or the deflection angle, which we'll be talking a lot. So that's a GIF of the lensing. Yeah, and one last thing we'll be discussing about in this presentation is that the shadow of a black hole. It's the thin accretion disk plus lensing effect together will give the appearance of a shadow. So due to the emission region that is geometrically thick but optically thin. So what does that mean, geometrically thick and optically thin? It means that it appears to be thick and it appears to be wide enough for light to keep passing through. But optically speaking, there is not enough matter in it to scatter the light. So that's what it means, geometrically thick, optically thin. So the light can still pass through without being scattered much. And it is accompanied by a distant homogeneous isotropic emission. So when you say black hole, the first image you think of with a black center with a bright surrounding is what is distant homogeneous isotropic. It is defined as the critical curve interior. It separates the capture orbit spiraling into the black hole and from the scattering orbits that swerve away. So it basically draws a line between the ones that are coming in and going away. Of course, there are some that are stuck in orbit forever, which can not escape at all. So those are defined by the critical orbits, which we'll talk about later. But for now, the photon orbits and the instability of it is described by the entering and exiting photon orbits. So this is the Event Horizon Telescope. And we see the Event Horizon Telescope readings. And like I said, the first image that comes, especially after this, is the image of a black center surrounded by a bright emission ring. So that's what we remember. And this is the image of the same black holes, but just a little sharper. And this is because of the lot of the coning that has gone into the telescope and the improvements in it. So the accretion disk formed from the black hole gravity determines how the shadow looks. And anything unstable there or anything that is fixed there, it all comes down to that. And by attracting and trapping everything in its path, dust, photons, radiation, everything. And the size of the shadow is dependent on intrinsic parameters. Basically, it's majorly dependent on the mass and the charges around it and the spin, of course, and all these factors. And its contour, the contour of the shadow is determined by the orbital instability. The more number of unstable photon orbits, the more messy it will look. And of the light rays from the photon sphere, and it appears to be a dark two-dimensional disk to an observer, which is illuminated by a bright uniform surrounding. Okay, so this is an introduction to the Gauss-Bonnet theorem itself. So this relies on the fact that the deflection angle can be calculated using a domain outside of the light ray. So we'll discuss more into why we do that. And the interesting part about this is it utilizes the subtle property of differential deflection, which we spoke about in weak lensing. And that is why this theorem is particularly apt for the calculation of weak lensing parameters. It gives a relationship between the geometry and topology. And this is the equation. As you can see, we have Gaussian curvature, we have geodesic curvature, and we have the Euler characteristic. So this is geometry and that is topology. So it's beautiful how these two are connected in a way to see that the connection can actually give us an insight to the body itself and the geometry around it. And depending on various factors, we can change and adapt it. So for the space-time geometry described by ds square, we see the curvature there, and this is the Gauss-Bonnet theorem. So why we use this? Like I said, it's connections between geometry and topology, and we link the curvature of the surface to its topological characteristics. Basically, the curvature to the Euler characteristic, and which gives us a lot of freedom to include a wide variety of surfaces, including boundaries, higher dimensional generalizations, and a lot of cosmological entities in itself. So theoretical consistency and elegance of the Gauss-Bonnet theorem arises naturally in the low energy effective action of the string theory. The low energy effective action is out of scope of this research, but it gives us a realization as to how perfect this fits the analysis for black hole theories. And the practical applications lies in thermodynamics and entropy that can be derived from the action. Yeah.
Just a question. When you say that it's arise naturally in string theory, so
Yes.
in all string theories?
The action that is specifically defined for what gravity theories. Yes. So we have the line element here defined for a 4-dimensional radial coordinate spacetime, and we have D is the chosen in the equatorial plane of optical geometry to apply the Gauss-Bonnet theorem, and for an asymptotically flat spacetime, we know the observer and the source are very far away from each other. So D is connected by a region. So we'll have a pictorial description of that in the following slide. And observer are connected by a differential domain. So the boundary of the differential domain is generated by the smooth particle. And these are unit speed vector, unit acceleration vector, and the circular curve. So the only drawback of the Gauss-Bonnet theorem is a major drawback of the Gauss-Bonnet theorem is it requires smooth surfaces. So when it requires smooth surfaces, we need to make sure that the domain we choose is smooth. So we first choose the boundary and we have a circular arc, all arc, making sure that it's smooth. So the central black hole is located outside D, meaning that we can exclude singularity from this region. Yeah, so this is the representation. We have the source here, observer here, and the black hole is outside the domain, meaning that the singularity is also outside. We don't have to worry about that. And we have the circular arc there, and we have the smooth surface here. So the differential domain we have chosen this here. So this is applied to the next part of the process, which is the Gibbons and Warner method. So that it reduces the complexity of the Gauss-Bonnet theorem, and the source at infinity is viewed by the observer in an asymptotically flat spacetime. The mass distribution exhibits spherical symmetry and functions as the lens, which is why the lensing is important here. And the optical geometry is obtained from the 4D spacetime. So we impose this condition to the null constraint. So basically, we take the line element as 0, and we take dt square, which gives the optical metric, and it reduces the line element to that. So we have here a smooth curve, which has the unit space condition 1, and we have 4 different terms in the equation of the Gauss-Bonnet theorem. So each one is analyzed here. First, the Euler characteristic. It is defined by faces minus edges plus vertices. It's the topology to structure. So we have 1 face, 2 edges, 2 vertices. So we have Euler characteristic 1. And so this term becomes 2 pi. Then we have the second term for exterior angles. So we have 2 discontinuous points there and here. And theta 1 and theta 2 together becomes pi. And so this one and this one together is again 2 pi minus pi is pi. And the third term is geodesic curvature. It measures the curvature of the curve. How much the curve curves is how much geodesic curvature measures. So we have K here. And when we expand this term, it expands into the derivative of C dot R, and it expands into this second term here. The first term gets cancelled out because we take this as a smooth curve, which is constant, and the derivative of a constant is 0. The second term from Christoffel symbols, we calculate it as R. And dt, calculating it is a little tricky because we are taking it R as the distance from the origin to the observer. So together, when we combine, we get this d5. And finally, when we put all this together, we get this one. And when we integrate from 0 to pi plus alpha, we get the deflection angle as that small equation. It's derived all the way from Gauss-Bonnet theorem through that small equation. So the aim of this research with all these in mind is that I want to say that it is to reduce the assumptions as much as possible so that we can have a more accurate archive to look into as we build on more theories. So the Gauss-Bonnet theorem is written as this, and the deflection angle through the Gibbons-Werner method becomes this one. But we should remember that the Gaussian curvature is always negative, so it means that the geodesics should locally diverge. Yeah.
I just have a question about the sum of the two exterior angles. So you say that it's equal to pi, but just if we are in a flat space at the infinite in the both.
Yes, because we are assuming asymptotically flat from the source to the observer, so it kind of reduces to pi. Next one, please. So I would like to start off with the methodology of what we'll be doing with the Schwarzschild black hole. First, in vacuum medium, we know the function f of r is 1 minus 2m over r. And we have the line element here. The first, we calculate the Christoffel symbols. Then, using them, we calculate the Ricci scalar, which gives the Gaussian curvature. Next one. Oh, yeah. This is the Laplace function for this f of r. Basically, we have changed the m here. As we increase the m, we can see how it doesn't look like much of a difference, but it plays a major role in shadow, as we will see later. So Christoffel symbols gives r, and all these together, we find a negative Gaussian curvature, as we predicted. So here we use a straight line approximation. First, we take this to be in an equatorial plane, meaning that theta is pi by 2. So that gives our d theta term to vanish altogether. So if d theta is vanishing and it is in the equatorial plane, it is one of the solutions. It is not to be generalized in any way. It is just one of the solutions. So for straight line approximation, it is actually supposed to be b over sine theta, sine phi, and b is the impact parameter, which is the perpendicular distance from the lens to the light trajectory. So when we do this approximation, we find the deflection angle directly reducing to 4m over b, and that's the deflection angle of a Schwarzschild black hole. So for a Schwarzschild black hole surrounded by massive particles, so this is the next case. First case is vacuum. Second case is surrounded by massive particles. So while calculating for massive particles, we will use the Jacobi metric, in which we have the energy and the mass function multiplied as a factor of f. So to determine the circular photon's orbit radius at the equatorial plane, and an asymptotic observer perceives one of the conserved quantities E as a function of V. So as V increases, we'll see that effect in E, and as m goes to 0, it goes to the light approximation, which is dl square. So we have Gaussian optical curvature. For this, as we can see the evolution of the V square term there. And again, straight line approximation applied, we get the deflection angle. So it is interesting to note how they evolve separately and like as different entities altogether. And that's going to keep continuing to happen in all the medium. So next medium is the vacuum medium. We have the Einstein angle, and we have R is defined as 2gm over c square. And the deflection angle of a photon in vacuum, it does not depend on frequency or energy. So the gravitational lensing in vacuum is generally achromatic. So when there is plasma, however, the situation changes. So presence of any medium significantly alters the dispersive characteristics. So when the plasma is there, matter falls into a black hole, it collapses and experiences substantial heating. So this heating reaches millions of temperatures, and that gives the formation of plasma. And this gives the whole medium being present around the black hole, which gives the change in deflection. In outer space, light rays travel through plasma. So it is very important for us to understand these effects, and photons undergo various effects. And because of which these become chromatic effects. And Yeah, it's no longer. So for lensing, the main interest is the change in the deflection angle due to the refraction that's happening due to plasma. So when a light ray strikes the heated mixture of ionized homogeneous gas, it refracts the implying the presence of a refractive index, and it reveals an essential factor. So these are no longer in homogeneous isotropic and everything. These are transparent in one inhomogeneous medium, and they start propagating in curved trajectories. It is not related to gravity or relativity, but we can calculate it using a refractive index n for an optically non-homogeneous medium. So for a Schwarzschild black hole, the optical metric is defined as this, and we have the frequencies each defined individually. And finally, we get the black hole in plasma medium, affected by plasma medium. And as we can see, if this term becomes zero, this reduces back to the Schwarzschild black hole. So one last medium is the dark matter medium. Dark matter, we know, is the invisible form of matter. It makes up most of the mass in the universe and creates underlying structure. Its gravity drives normal matter to collect. One very distinct characteristic about weak lensing is that it is very useful in recognizing dark matter distortions. So that's why we study dark matter as a matter effect. And it builds up into stars and galaxies through dark matter. It is an invisible material and hence cannot be seen. So it mathematically accounts for the nature and placement, which helps us understand deflection angle more. So this is an image from NASA's telescopes, and we can see the effect of dark matter in each of this, and the lensing is particularly visible in all these. So for defining the dark matter as a medium, refractive medium, we use this these equations. And when we calculate the final dark matter, we effect due to deflection angle due to dark matter, that is the final equation. So all this is due to, this is only for Schwarzschild. So we have 4 different black holes to apply for. So we will see that. So as a graph, we have the Schwarzschild rays for mass as 1. And as mass increases, you can see that the effect of the impact parameter to deflection angle increases as well. And that's for the presence of massive particles as a medium. And this is for plasma and for dark matter. I think the graph was not there. Yeah. So these are the 4 different scenarios that we'll be discussing for the other 4 black holes. So here we have taken Z as a parameter to vary the frequency ratio. So the first one is the extended uncertainty principle black hole. So this one is more it invokes a lot of quantum mechanics in its formalism. So information paradox is a fundamental puzzle, and Hawking proposed the dissipation of matter through quantum fluctuations. So that is the inspiration for this formalism. So as a quantum entity, black holes were related to Heisenberg's uncertainty. So basically, the information paradox, as we know, is if everything into the black hole goes, then where does the information go? Quantum mechanics predicts that it cannot get lost. So it has to be preserved somewhere through something. And we have a coupling parameter that shows up in the uncertainty principle, so we will use that. So the generalized uncertainty principle prevents a black hole from dissipating by including an additional term, which is the coupling constant, and it's proportional to the square of momentum uncertainty. Alternatively, the extended uncertainty principle is obtained by an additional term proportional to the square of position uncertainty. So it's delta x delta p is greater than or equal to 1 plus alpha times delta x square over L square. And alpha is the extended uncertainty principle parameter, which is the coupling constant. So using that, we form the function here, and we have the weak deflection angle. Again, it's evolving independently, meaning that if alpha is 0, it reduces to Schwarzschild. So this is the lapse function for f of r, and we can see that alpha has a pretty significant influence, especially when it's over 1. So we have the plasma medium calculations for the refractive index. And when we find the deflection angle, again, it's different terms, plasma effects separately. And so this one, I would like to point out that if these two are taken separately and we combine it into this factor, this one corresponds to the post-Newtonian limit. And this is particularly evident when we are calculating observables. Next one. So I'll talk about that in a bit. Yeah, so we can see the effect of the impact parameter. So we have the Schwarzschild case with 0 alpha and 0 unity refractive index. And as alpha and n increase, we can see that the peak itself goes up. Although it's not much of a difference in the impact parameter side as it goes down, but on the lower impact parameter side, it's higher. Yeah, so we can see the terms, the post-Newtonian limits here explicitly. So this is important to know because we can see how prominent that one particular factor in itself is.
Sorry, I have a question about the plasma. So what's the optical depth for this kind of plasma? So there is a really possibility to have photons arriving from the back, the back and just cross the plasma and not scatter on anything and just continue to.
Yes, that's why we take a geometrically thick and optically thin area of consideration, because when we include plasma in that equation, we don't know how it's, like you said, how it's going to behave, where it's going to come from, and all that. So we consider that for minimal scattering.
Okay. So at the end, you consider like a fraction of photons arriving from the back.
Yes.
And mixture with the scattered one.
Yes.
Okay.
So next black hole is an asymptotically flat black holes in Hornetsky theory. So we start by gravitational force from Newton's centuries ago. It's all basics again. So we have the gravitational constant G, and Einstein's relativity suggested the universe was finite and spherical, but G exhibits a dependence. And it depends between, it's dependent on the mass distribution and the size of the universe, where G accounts for the inertial forces. This was the first formulations. But as we found out the universe was expanding from Hubble, we found that the universe was no longer the same, it was no longer in the same place. So it means that the mass distributions were not reliable, because it had a probability of an infinite universe, but it was limited by the possibility of it was limited by the finiteness of the speed of light. So that means that the mass distribution and the size of the universe is always changing, and we cannot rely on mass distribution to give us an account of G. So that means the gravitational constant changes with time as well. So this can be fixed by, one of the possibilities of fixing it rather is to taking G as a scalar field. So the metric field contains gravity in the form of a tensor. So consolidating the scalar field with the metric gives us the scalar tensor theory. So one example inspired by the Lovelock theory of gravity is the Hornetsky theory. And it's a 4-dimensional space-time. Its scalar field is incorporated as a new degree of freedom, second-order field equations of motion. And all this put together, it will give us a good consolidation of scalar field with the metric. So applications are gravitational waves, acceleration of the cosmic system. So we have the black hole, the Hornetsky black hole in an asymptotic flatness. So gravitational field approaches 0 at large distances, we know that. And asymptotically flat black holes basically mean that the black hole space-time is static and space is spherically symmetric, reduces to the Schwarzschild space-time. In this case, it reduces to the Hornetsky black hole itself, because we are talking about Hornetsky theory in particular. So for an asymptotically flat black hole, the line element is defined as this. And h of r, we can see the function here. And the deflection angle comes out to be this. And again, k is a very dependent factor here, but we can always take it out and consolidate it back to the Schwarzschild metric. But one thing to remember is mu is no longer mass here, it is a mass function. So that is something worth mentioning. So this is the lapse function. K is pretty consistent with its nature, but we can see mu is a little more, it's more closer, that's more less abrupt than K, but it's more spaced out. And we can see that the refractive index for asymptotic black holes, the same formula as the ones before, and the corresponding computations give the deflection angle. Yeah. The results here, we can see that K being negative shows a negative deflection, which is not really useful for us, and we have the positive deflection there. So it has to be over 0. And we have the changing of K with higher amounts of change, and you can see that it's more abrupt between 0 and 25, but as it goes higher, like if you calculate for 100 and 200, it's going to be way more closer. And for plasma, we can see again. So we see that it is a little more, its refractive index, it's a little close together in the beginning, but as you reduce the refractive index, it reduces. The more you increase it, the more it. So the next black hole is the Reisner-Nordstrom black hole, and we have a magnetic correction with Einstein nonlinear Maxwell fields in it. So we start with the Big Bang to black hole. Singularity is always a problem. We know that it hinders general relativity from being unified to other models of the universe, and the black hole solution without singularities is presented by nonlinear electrodynamics. So for nonlinear electrodynamics, we take analytical black hole solution like the Born-Infeld type corrections and the linear Maxwell theory in the weak field limit especially. And it's an attempt to eliminate singularity. So the governing equations are, okay, the equations are missing. Okay, so we have space-time tensor and electromagnetic invariant, and we have Lagrangian density and energy momentum tensor. These are the 4 important ones, and we'll start with the electromagnetic invariant in the next one, which is this one for this particular case. And we have ds square defined, and Lagrangian is defined here, and the tensor is energy momentum tensor is given here. So P here is the magnetic charge, and B is the parameter, coupling parameter with the dimensions of length to the power 4. So we solve for the energy momentum tensor, and we reduce the field equations. And from the Einstein field equations, we end up with the function here, which gives the deflection angle in here. So we have corrected it for the higher order magnetic charge. So we have more terms of P. And also it is interesting to notice that B doesn't show up till the 4th order of P. So we can see how little influence it has. And you can see the difference here. So this is the Schwarzschild case. And this is the difference that B makes, especially in lower radii. So we have the deflection angle in vacuum in the previous case, and here we will see that for the massive particles, we have B terms segregated out from the main deflection angle equation. And then plasma case, we have this very long equation, and then dark matter medium. Again, B terms and U square, V square, V and W square, sorry. And we have the equation for deflection for dark matter. So in this one, we have changed for different values of beta from 0 to 10,000. And the the difference had to be that much for it to show any change in the values. So we can see how much it is converging here. But in the case of P, it is relatively more uniform in the change. But it starts off at a peak and then reduces as it comes to the Schwarzschild case as the P increases. And we have for the massive particle case, we'll see a little later that how this really is very close to the Schwarzschild case itself and how that can be a possibility. And then the plasma case. So the line that goes here is for the mass of 1.1. Others are taken for a mass of unity, and this is for mass of 1.1. The black dots are for mass 1.1 for the Schwarzschild case, and the green is for mass 1.1 for the RN black hole, which is not the same, but very close. And then the dark matter medium, we have a very wide spectrum of where it's starting to where it's. And we have the effect of magnetic charge cannot be generalized, unlike electric charges. So this is a very important or a very interesting premise for the calculation of shadows. So for equatorial plane, we have the Hamiltonian-Jacobi approach, and we have the critical impact parameter, which I spoke about earlier. So we have the critical impact parameter as the angular momentum to energy ratio, because it manifests itself as a constant of motion. So we have the B critical here that shows the distance. So we will be calculating that for the shadow. So we have the conservation equation here, energy plus potential energy, kinetic energy plus potential energy. And we have V, and this constraint is defined, has to hold for us to be able to proceed with the calculations of the shadow calculations and for plotting the shadow. So we have the orbit equation here that is derived from the constraints mentioned, and from the line element, we define the Lagrangian for the line element, and from there we define we derive the angular momentum and energy, which gives the relation here, and which reduces to all that. Using all this and these equations, which is for the emissivity of the plots. So magnetic charge tends to increase the curvature of the space-time, as we can expect, and it results in more photons being pulled, and it decreases the radius of the shadow. And black hole spin, magnetic charge creates two distinct horizons. So really, inner and the outer horizons, the inner one is really critical, the outer one is a little more unstable. So negligible charge, they are one indistinguishable as the charge increases with the critical line. Yeah, and these becomes more prominent. So we use the radius, and for this particular black hole, we find this equation to look like this. So while we plot this, we get the shadow. It's the ray tracing, actually, the geodesics of the rays, and we can see that as it is the critical orbits are a little more constrained than the unstable orbits. And yeah, next one. So we have the constraint of a black hole charge. The shadow size depends on the physical charge, and such as the electric, star, scalar charge, magnetic charge. And we use the EHT M87 image to post these constraints to an error of about 70%. And the physical charges gives the radius of the horizon itself to be a little bit with the uncertainty of that. So this is the constraint that it poses. So you can see that it goes a little away from there till there it's well into the mark. So the accretion disk is dynamical and spherical, as we spoke about. And the number of orbits are considered throughout the spherical accretion and not just at the equatorial plane. We are no longer constrained by the plane itself. So we take about the 4 velocity and we calculate the redshift factor. So which will give us the shadow of the black hole, the emissivity parameter, this one. So we can find out the emissivity per unit volume. We have the infinitesimal distance, and here the observed flux. So all of this put together, starting from the energy equation till conservation of energy equation till here, we get the parametric plot of a black hole appearance. So we get this. So this is for the case of vacuum. We see that the peaks correspond to the high brightness here, and the low points correspond to the black hole itself. And this is for the plasma. So you can see that the plasma has, to answer your question, the plasma has thickened that part alone. So it looks like it is still geometrically thick and optically thin place, but it's no longer that because it is surrounded by plasma. So it manifests as light itself, but it's a lot of scattering and instability. So the last black hole, it's the asymptotic magnetically charged non-singular black hole. So again, going back to the problem of singularity, we spoke about how non-linear electromagnetics can change the perspective of singularity. So in this one, we will try to remove the singularity altogether by replacing it with a source that is exotic matter or some kind of field that can that we no longer know yet. So the extreme gravity and mass and density collapsing on itself all arise from there, but it is presumed that it is not the case because the field itself manifests like that. So the alternative structures, mechanisms at the center of non-singular black hole and barred by these regular black holes. And the quantum effects may cause it to be magnetically charged. So we have the line element, and the Hayward metric is defined as that here. So when we calculate the solutions, from the action, we find FFR here. Yeah. So we have the mass function derived from here, but we will not, instead of using the mass as m itself, we will use it as a function of beta here and as the electric charge that shows up. So we'll use it as a function. So these are the lapse functions. We can see that the changing of L shows the maximum effect and changing of beta shows the minimum effect. Yeah, so this is the function which we will use for N. So this was given by the authors who formulated this black hole in particular. So straight line approximation, we have alpha here in vacuum. Next one. So this is the graph. So you can see how L has barely changed at all, no difference. And we have hue that's changing a lot. It starts off at a very low minimum and keeps increasing towards the Schwarzschild case as it increases. And then we have the effect of the dark matter medium here. And we can nowhere see the blue here because it's probably in the negative side. And we have the red here, which is more towards the Schwarzschild. And again.
Sorry, you say it was dark matter split?
Yes. Yes.
So what do you assume to take into account the dark matter?
Sorry?
What do you assume? What do you assume to take into account dark matter here? Spherical halo?
No, it's just the fact that we are taking dark matter as a refractive index as a medium that is considered to be having a refractive index mentioned.
Okay.
And we have the constraint again. We have Schwarzschild radius and the shadow radius coming together. And again, the 17% error. And the parametric plot, the emissivity plot is here. You can see the very small changes here. But when we look at the black hole picture, the next one, you can barely see the difference. That's why emissivity plots are important because that gives the numerical interpretation of these. When you look very closely, maybe with a ruler in your hand and then measure each of it, it'll look like as it changes, it becomes smaller and smaller. So it's not very obvious when we look at it straight away like that. But this part, the bright part here, that's particularly similar here. So the yellow part is the one that changes very. So this is the consolidation of all results that were presented from here. We have the Schwarzschild case and the EUP black hole, the asymptotically flat black hole in Honesky, RN black hole, and the last one. So something I would like to point out here is that first one, the Schwarzschild black hole and the Rn black hole for massive particles are pretty much the same. So it's a good thing to think about how a magnetically corrected for higher order in Einstein nonlinear Maxwell field can be similar to the simple Schwarzschild case in the presence of massive particles. And then even plasma medium it's not the same, but the thickness appears a little bit similar, I would say. And another thing is I would point out the vacuum case of Rn black hole. You can see a tiny stretch there, and that comes closer. So when I presented the vacuum case earlier, it was plotted for a more larger impact parameter. But since all these are in the same scale, this looks very tiny compared to, let's say, this one. So it's pretty widespread, spread everywhere. And another interesting thing is the dark matter medium. Schwarzschild just goes from red to blue, which is small to big. But here we can see that it starts off red, goes down, becomes green, and then comes back up blue again. And here it's just the middle part of it. And here again, more towards the higher, but middle part of it, and it's the lower. So everything has a different evolution depending of weak deflection angle. So that can give us a good, an archive of what to refer to, like based on the future observations. We can see that if it is extremely spread out, we can always have this as an option. But the more constrained it becomes, we can choose this or this, and we can modify accordingly. So if it's a magnetic charge present, we can look into this, or if it's a plasma of the magnetic charge, we can look into this. So you can just like keep constraining it until we are able to find which theory suits the best. So to conclude, 4 different black holes were studied. Each individual factor showed a distinct consequence of the deflection angle. And all of them is prominent enough to differentiate one from the other. And if they are same, it's even more, it makes us even more curious, because how can that be, right? So with similar behaviors being distinguishable at one particular range, and the calculations were done with way less assumptions. It was tried, more factors were tried to be included so that the assumptions would be less, though it became complicated a lot of times. And these suggest that the theories built from these results could be more accurate. And it will be followed by further modifications to gravity. So the more gravity theories we can get, and the more constraints we follow, can even stretch out to post-Newtonian limit, and we can even talk about gravitational waves in that matter. And along with the study of accretion and how it affects the other gravity-related theories and entities. So currently the astrophysical parameter uncertainty dominates gravity theory parameter uncertainty. And this underlines the importance of understanding the accretion model. So if EHT is used to be successful to test gravity theories of gravity, we can always use that word our advantage to fine-tune our modified gravity theories more. And these theoretical developments will allow computational inexpensive frameworks to produce high-resolution images, photon rings based on GR, and that will help us modify shadows more. And yeah, so we can do it in a fairly astro-independent way. And yeah, so we have a lot of pending data to be released from the EHT team, LIGO team, and the Virgo team. So all of that can help us understand modified gravity theories more, and it might help us understand the shadow asymmetry more as well. The more they zoom in on the image and make it clearer. So next one. So yeah, it was the shadow radius was used to constrain it to the 17% error, and it can further be used to constrain more gravity theories. These constraints are about 500 times more stringent compared to the solar system models, and they perform better tests. Thank you for listening.
Thank you. Questions? Or Please, Sebastian.
So just to go to the observations.
Mhm.
So do you have the possibility with the actual pictures to have like there's a possibility to really try to discriminate between Gauss-Bonnet and GR?
We
Or
cannot do it with 100% accuracy for sure, but the more we start to observe how the black hole is behaving, because it's a dynamic system at the end of it. So the more we constrain, the more accurate we can polish our system. Can never be 100% accurate.
so do you expect to have some other frequencies observations in the future to have a test of what
It depends on what you want to measure. So if you're like interested in particularly plasma and how it affects, and or like say even gray body factor or things like that, where you are explicitly dependent on frequency, so you might.
but if you have different frequencies and we take it into account,
Mhm.
so can you expect to reduce the errors? Because okay,
Yes.
you show a very nice picture, but it's not a real, it's a really illustrative picture.
Yes.
And even more when you show the thinner, so the base picture is with a kind of machine learning
Mhm.
trained on some expected.
Mhm. Mhm.
So probably it's not in favor for those
Sure.
model in this case.
Yes. Yes.
So to have different kind of pictures to try to reduce noise, just adding co-adding images
Mhm.
should be a good stuff.
Yes.
From the people online, please, if you have any questions, just use your mic directly. I'm on a wait 30 seconds. Someone here?
That I can have.
Yes, yes, please.
So you mentioned these weekends. So do you expect to have some differences in frequency signal? So using Gauss-Bonnet, and the side question is because calculation of frequency is pretty hard
Mhm.
to do when you have to convolve with everything with numbers of the mass solutions and stuff.
Mhm.
So can you expect to have some free parameters and still be able to have a frequency prediction?
I haven't thought about that. It is possible to, I don't know if you, by what do you mean by free parameters? Do you mean for gravity theories in particular, or like
Yeah.
post-Newtonian limits?
Yeah.
Yeah.
Okay.
Yeah. So the thing is, as we add more parameters, it is going to get more complex, because in this, if you saw all the black holes had f of r defined for f minus f of r dt square, and the radial coefficient will be the inverse of f of r. So when that changes, when the coefficient of dt square and dr square change, it is going to pose a complexity, because most of the parameters that we calculate, like refractive index and even shadow, we start off with the coefficient of dt square. So that's not going to change. So, but how will you include the effect of dr square then?
Yeah.
So how is it going to be different? So,
Yeah. Because in fact, what we do, in fact, is to use a sheet mass.
yes.
And so, and we have to assume something, so number of Eigenweight or isothermal one. So we have a lot of approximation just to evaluate the frequency with the actual data, for example. So if we do that, it's still okay to have another kind of other sheet mass approximation using Gauss-Bonnet model, for example?
Yes.
Okay.
Is there a way in which you can actually reproduce two features, well, same features of, say, the shadow of a black hole using two different theories? I mean, because we usually think that two different theories of gravity will reproduce a different shadow, but I'm never quite sure whether two different theories will reproduce the same one. And if so, can you think?
Probably not to the zeroth scale for sure, but it could be possible to do that if we are going to stick to the numerical method. If you are going to stick to a strictly generalized method, it is going to be complicated.
Why do you think the numerical method will do that? Because we have to make an approximation somehow?
Yeah, so that's the problem with the numerical method, because we'll have to include more approximations, but that will at least tell us if we try to make those approximations and try to match the results between two theories, maybe that will show what is so different between two theories. And maybe we can work our way up from there.
Okay.
Well, I don't see more questions, but let's end this here again.